Hello and welcome to the second talk in our Virtual Astronomy week. Stars have fascinated people for millennia, and many human societies join them up to populate the heavens with gods, creatures, people and all sorts of things, although it has to be said that this does require a fair degree of imagination. The philosopher Auguste Comte held that stars were a prime example of something that we would never know what they were made of. Fortunately for us, he was wrong, and we now know a good deal about stars and our closest example, the Sun. So this talk looks at what stars are, how they work, and how they change throughout their lives, and by extension we'll also look at what will happen to our own Sun. So, here goes. Almost all the light we have on Earth is directly or indirectly from the Sun, our local star. And if you remember from the first talk, light takes 8 minutes to reach us from the Sun, but 4 years from the next nearest star. And from the most distant in the universe, it takes billions of years. But near or far, most of what we know of stars is from their starlight, hence the title of this talk. Viewed through a telescope, a bright star looks like this. This is the star Vega. It's visible overhead on summer nights, and its light takes about 25 years to reach us. So it's one of the closest stars. As seen from here, it's actually just a point of light. All of these things, again, let's try and find where my cursor's gone. All of these things here, these rays, are artifacts of the telescope that was used to take this picture. So, and in fact, even through the largest telescopes in the world, almost all stars appear as just points of light. And yet, we know what they're made of, why they shine, their past, their future, and in many cases, whether they have planets going around them. And we can tell all of this from their light. Let's start with something obvious. Here's the first picture again. Have a look at it and see what you notice. Hopefully, two things. The stars have different brightnesses and also different colours. There's quite a red coloured one. Brightness depends on a couple of things: how intrinsically bright the star is and how far away it is from us. And the intrinsic brightness of a star is called its luminosity, or astronomers call it its absolute magnitude. Vega, for example, is 40 times as luminous as the Sun, but doesn't appear as bright because it's over 1.5 million times further away. So that's brightness. What about colour? What does this tell us? The colour of a star depends on its temperature. Cooler stars are red, hotter stars are blue. The Sun is about 6,000 degrees. Vega, as a comparison, is 9,600. That's the surface temperature, by the way. Central temperature is more like 15 million. So what else do we tell from starlight? Well, here's a short experiment. It's a movie. And Isaac Newton of gravity fame did this and more in 1666. He used sunlight, but I've cheated and used a torch. So I'm shining some white light from the torch through a glass prism and seeing what comes out. And you'll notice when we get there that we actually get a nice rainbow of colours. And to make it a bit more obvious, here's a diagram to show clearly what's going on. So, 1666, as I said, Isaac Newton shone sunlight through a prism. Now, this phenomenon has been known about for a long time, the actual production of all these colours. And the conventional explanation was that the prism itself was responsible for producing the colours. But Newton worked out that if this was the case, he ought to be able to isolate one of the colours, say red, by drilling a hole through that screen, pass it through another prism, and get some more colours out of it. And this, in fact, is what he did. But he didn't get any more colours. Newton correctly deduced that this was because the colours are actually an intrinsic property of sunlight. It's not the prism that's producing the colours are already there in the light, in the white, like whitish light from the sun. All the prism is doing is just bending that light of the different colours by different amounts, so it's analysing the light. Here's a pocket spectroscope. You point this end at a light source and look through this end. And this is a sort of more compact version of that prism arrangement that we saw previously. And if you point it at some sunlight, the sort of thing that it produces that you will see is this. You get a continuous band of colours, the rainbow, and that's called a spectrum. But look closely at it and you'll see that it's crossed by many narrow dark lines. And these lines in the spectrum of the sun were discovered by Wollaston in 1802, and more were described by Fraunhofer in 1815, and actually unfairly then they became known as Fraunhofer lines. In fact, there are hundreds of them. A high resolution spectrometer shows them like this. And this is such a big long spectrum we've had to put it into little slices and put them below each other. However, the nature of these lines, what was causing them, remained a total mystery until about 1860. Now, have you ever tried sprinkling some salt into, say, a gas flame on your cooker? If you try that, don't try it too much, you'll notice that it burns with an orange light. If you pass that light through that little spectrometer I showed you, this little spectroscope, you'll get the result something like this. This line here. Salt consists of the elements sodium and chlorine. And down here, third from the top, you can see the spectrum produced by heating up sodium. And there are a number of individual bright colours, and they're called emission lines. And in fact the two brightest ones are here. There's two there, they're just very close together. They're called the D lines, the sodium D lines. And this is why heating up salt produces an orange flame, because the bulk of the light is coming out here in this narrow band of colours. And it's also why sodium streetlights are orange. And for your interest, we've also shown the result of some spectra from other elements, heating up other elements. So magnesium here at the top, and hydrogen, and calcium, and iron. Now let's compare these with what we see from sunlight. Here's the sun spectrum. Okay, and in particular I want you to look here and here. You see there's a match. The dark line here in the sun spectrum matches this line here in the spectrum of hydrogen, and this dark line here matches this line here in the spectrum of hydrogen. Okay. So can we say that these dark lines that match these hydrogen lines indicate that hydrogen is present in the Sun? But if so, why are they dark? And well, the answer to this came when it was realised that surrounding the Sun's photosphere, its bright surface that you see, there's a layer of cooler gas, and it's called the chromosphere. And the photosphere, the bright bit, emits whitish light, but the cooler gases above the lower layers actually selectively absorb the same colours that they would emit when heated. If you just look at the chromosphere without the Sun behind it, you'd actually see emission lines, they'd be bright. Okay, but because it's a bit cooler than the photosphere behind, they look dark against it. Okay, and the chromosphere is about 2,000–3,000 kilometres thick. So we now have a means of finding out what the Sun is made of, or at least the sort of gases, some of the gases around it. Look at the lines in the spectrum and try and decide which elements they come from. It's a sort of stellar barcode. So, in principle then we can tell what the Sun is made of, but what about stars? They're fainter, they're much more difficult. And visually, this was actually achieved in the 1860s and the 1870s. And the main man who did this was William Huggins. And this is his telescope. And if you look down here, there he's got a spectroscope. The light is coming down here, going through actually two prisms. I'll show you the arrangement, this one, and then out through an eyepiece. If it's clear this evening, go out and have a look almost directly above you, and you'll see the star Vega. Okay, the same one that I showed a picture of earlier on. And it was a major milestone when the first photographic spectrum of a star was obtained from Vega in 1872. And I guess it was around about this sort of time when you could say that the science of astronomy became the science of astrophysics, when astronomy changed from measuring the positions of things in the sky to working out what they were made of and how they behave. Anyway, enough of building up the dramatic tension. What were the actual results? Well, for the Sun, it's about 3/4 hydrogen, 1/4 helium, and various bits of other things. Helium was actually first discovered in the Sun in 1868 by Norman Lockyer and Jules Janssen. In fact, his name suggests that it's from the Greek helios for sun. Now, stars aren't all the same in their makeup, and this is reflected in their spectra. And as an example, here's some spectra of different types of stars, and they go from hot up here down to cool down here. Hot, cool. And astronomers assign a spectral class to each star, which for historical reasons follows the sequence O, B, A, F, G, K and M, hottest to coolest, and within each class there are finer divisions labelled 0 to 9, with 0 the hottest. And the Sun is of type G2, so it's sort of around here somewhere. And notice that the cooler stars, okay, actually have more helium. Here's the helium line. And actually some of them are cool enough to have lines of molecules rather than just atoms. So we know what stars are made of. So the next question is, what makes them shine? Where does the energy come from? So, what keeps the Sun shining? Well, for many years we didn't know. Various suggestions. Chemical reactions, for example, sort of burning or something like that. Well, you can work out how long the sun would last if it was chemical reactions, and it would last a few thousand years. How about something more subtle? Suppose it was shrinking. As it shrinks, it releases energy, gets hotter. Okay. How long would the sun last if that was the case? A bit better, 25 million years. Now this is all very well, but around about this time it's known that the age of the Earth is at least a few billion years. So none of these were actually on. And it wasn't until 1927 that the British astronomer Arthur Eddington suggested that what was happening, given that you had all this hydrogen and helium, was that hydrogen atoms were combining to produce the helium. And he wrote the following: "To my mind, the existence of helium is the best evidence we could desire of the possibility of the formation of helium. I am aware that many critics consider the conditions in the stars not sufficiently extreme to bring about the transmutation. The stars are not hot enough. The critics lay themselves open to the obvious retort. We tell them to go find a hotter place." Eddington was actually right. He didn't know the details of how this was happening. That came later. But stars and the sun shine as a result of nuclear reactions going on in their centres. They are in fact fusion reactors. And in fact, as he suggested, 4 atoms of hydrogen are combining in such a way as to form 1 atom of helium. In fact, it probably won't surprise you that it isn't quite as simple as simply pushing 4 hydrogen atoms together, or 5 hydrogen nuclei together strictly, and standing well clear. For stars like the Sun, the following is actually the dominant reaction. There's a whole chain of nuclear reactions. Okay, here we start with hydrogen. 1, 2, 3, 4. 2 of these get together to form, in effect, deuterium. That's sort of heavy hydrogen. That combines with another one to produce a slightly lighter form of helium, 2 of which collide, throw a couple off in order to produce the final version of helium. Now, this step is actually very unlikely to happen. Most of the time, these 2 collide and then fall apart again. Okay. Typically speaking, this step takes about 1 billion years. Conversely, this one takes a few seconds. Now, it's actually fortunate that this one is so unlikely, because if it went much more rapidly, the sun would have burnt out years and years ago. And the other significant point to notice from this is these are gamma rays coming off, and this is energy. So we get energy out of this reaction. And in fact, if we measure things, suppose we tot up the masses of these 4 hydrogen nuclei and compare it with the mass that we get out at the end, then they're heavier. And the difference in mass between those has been radiated away as energy. There's a famous equation that Einstein produced, E equals mc squared. Everybody knows it. And it's saying that m in this case is the difference in mass between the 4 hydrogen atoms and the helium. And that gets converted into energy, which is what powers the sun. Now, as a result of that, the sun is actually losing about 5 million tons of mass every second. And all this is going on in the core of the sun. The energy released by those reactions then takes somewhere between 10,000 and 160,000 years to actually make it to the surface of the sun. It's quite a slow process. And then 8 minutes later it reaches the Earth. In fact, the Earth gets about 1/2 billionth of the Sun's emitted energy. So that's where the energy is coming from. So there's one other question. What holds stars up? They're balls of gas. Why don't they just collapse under their own weight? And again, the answer is these nuclear reactions. The nuclear reactions going on at the core of the Sun, where it's 15 million degrees or so, produce a pressure pushing outwards. And it's that balances the mass of the Sun, the rest of the Sun, trying to collapse inwards. Now that means that if reactions were to stop, the core of the Sun will collapse, followed shortly after by the rest of it. And that will have important ramifications, as we shall see. So there's a pressure balance, is what to remember. Alright, we're now at the sort of stage where we can do a life history for the Sun, and in general for most stars. If you look below the belt in the constellation of Orion, here, you will see a faint fuzzy patch of glowing light. Okay, and it's called the Great Orion Nebula, or M42. If you look at it through a telescope, then it looks like this. I think I showed you this picture yesterday as well. And if you look at the spectrum coming out of all this gas, it's largely hydrogen. It also contains lesser amounts of heavier elements, including what astronomers term dust. Now, if you look closely, you can see more or less in the middle, sort of around here, there's a little group of stars. And in fact, it's these stars that are responsible for lighting up this cloud of gas. It's called a nebula. And an obvious interpretation is that these stars are formed out of that surrounding gas by gravitational collapse. You've got all this gas, something disturbs its equilibrium, and then you just sort of sit back and watch. Okay, we've got another example here. This is part of the Eagle Nebula. Same sort of thing going on. New stars forming. So what is it then that actually provides this initial kick, this disturbance you need for these clouds of gas to start collapsing? Well, various things can do it, nearby explosions, or even galaxy collisions. Galaxies, at least in groups, are actually relatively close to each other for their size, and occasionally they bump into each other. Here's an example. Here's two galaxies have actually interacted gravitationally, and you see these bits, that sort of blue streak there, and another group here. What's actually happened here is that this disturbed some of the clouds of gas in those galaxies, triggered a whole new bout of star formation. So we get a lot of hot, newish stars, which are blue, and then the gravitational effects have actually slung some of those off, like that and like that. There's another example here. Okay, see, this galaxy has been disrupted almost entirely, but lots of new stars. Now, in our own galaxy, about one new star a year is forming at the moment. For galaxies that have undergone a recent collision, the rate could be hundreds of times higher. So a galaxy collision isn't necessarily bad news. It actually creates new stars. Anyway, wherever the trigger, once started, a cloud of gas and dust starts contracting to form new stars. And I'm just going to show you a short movie of a simulation of this sort of thing happening, and you can sort of watch the stars form. So here's the cloud of gas, some trigger, and it starts collapsing in on itself. Just zooming in there. There's one forming, there's a group of stars forming, and notice that we get more than one. And that some of the stars are actually ejected out of the cloud, so they move apart from each other. And the net result, at least initially, is what astronomers call an open cluster of stars. So you get a number of stars relatively spread out. Okay, and let's move on from that now. And here's a good example. This is the Pleiades. These stars, which is one of the closest clusters to the Earth, so they're hot, middle-aged stars, and it's about 100 million years old. An astronomically minded dinosaur would have been able to watch these forming. And looking at the motions of these stars, we can tell that this cluster will actually have dispersed by about another 250 million years. So the next question is, did our Sun form in a cluster? If so, where's the rest of it now? Well, in 2014, a group of astronomers announced that this star, HD 162826, is actually, or likely to be, a sibling of the Sun. This star near Vega on the sky is about 110 light years away, and it actually has an almost identical chemical makeup to our Sun. And again, we can see how that star is moving, and we can extrapolate therefore its movement backwards and the Sun's movements backwards, and in fact they turn out to be about the same place, some 4.5–5 billion years ago. This star is actually about 15% more massive than the Sun, so it's slightly bigger and slightly hotter. It's got no known planets yet, but it may well have some. So what happens to our newly forming star then? We have a star and the gas contracts, and as it shrinks it gets hotter and hotter until eventually it's hot enough in the core of that gas for nuclear reactions to start. These nuclear reactions provide an outwards pressure which ultimately halts the contraction and the star starts to shine. Stuff that's left over from this then forms a sort of dusty disk around the star. Here's a selection. These are actual observed disks. And that disk forms into planets. Notice the empty spaces in all of these disks, these sort of gaps. Okay, and typically these gaps indicate where planets are forming. The planets are forming then sort of hoovering up all the material. And the existence of the material in these disks actually has an interesting effect on the motion of those newly forming planets, but I'll talk about that when I talk about exoplanets in the Is the Earth Alone in a later talk. But meanwhile, here's a closer look of a direct image of a planet forming. The light from the star has been blocked out here so it doesn't sort of overwhelm everything. And this in fact was the first confirmed image of a newly forming planet. It's around a young dwarf star, and the planet at this point has a temperature of about 1000 degrees centigrade. And it's quite big, it's a gas giant, it's a few times the mass of Jupiter, and is about the distance from its star that Uranus is from our own Sun. Okay, the whole lot here is about 370 light years from Earth. Now, disks appear to be pretty common in newly forming stars, implying that planetary systems should be quite common as well, and indeed they appear to be so. This is an image of 3 planets around the star HR 8799, and again the image of the star itself has been removed. And all of these planets are thought to be more massive than Jupiter and up to about 10 times further away from their star. But I said more about these sort of things in a later talk. Let's continue our life history of stars. So ultimately our newly formed star becomes a bit like the Sun. Okay, So the next question is to ask what happens as the sun ages. Here in the core of the star we are turning hydrogen into helium, and you can tell that the core has got much more helium than hydrogen, whereas in the outer layers the opposite is true. So what happens as we start using up the hydrogen? Well, a clue came from the work of two astronomers called N.J. Hertzsprung and Henry Norris Russell, and the year was about 1910. And they thought it would be interesting to plot the colour of stars, which if you remember is related to their temperature, against their actual luminosity, that is how intrinsically bright the star is. And what they got was not a random scatter. So here, where absolute magnitude is the actual luminosity of the sun, of the star, sorry, and luminosity here compared to the sun. So how intrinsically bright the star is, and the star's temperature from hot through to cool. Okay, here marked off as spectral class along the bottom, and as said, the sun is about here. Most stars, you'll notice, are in this diagonal band across the plot, and it's called the main sequence because most stars are on it. But there are other stars, okay, giants, supergiants, these little odd stars called white dwarfs, which are white and small, that's the name, and they have their own areas within this diagram. And eventually it became clear to astronomers that this represented a sort of evolutionary sequence. Stars form, originally cool, rather dim, and they move on to the main sequence. And there they stay until they start running out of hydrogen in their cores. So this band indicates stars that are currently turning hydrogen into helium. Astronomers use a sort of shorthand name for this. They call it hydrogen burning. It's not actual burning, it's nuclear reactions. Another thing that we need to know is that there's a relationship between a star's luminosity, how intrinsically bright it is, and how big it is, the star's mass. So the more massive a star, the more luminous it is. So all of these stars up here are very large. Okay, hence the name, supergiants, giants. Whereas down here at the bottom, they're all very small, they're generally dubbed dwarfs in some form. So the further up the main sequence, the more massive and luminous the star, and, as it turns out, the faster it runs out of fuel. The rate of the nuclear reactions going on in the core depends on the mass of the star. The bigger it is, the faster it goes. And here's a colour version of the Hertzsprung-Russell diagram. We've marked some ages now on this along the main sequence. Okay, so for the Sun the lifetime is about 10 to the 10 years, 10 followed by 10 zeros, 1 followed by 10 zeros. Okay, so further up, 10 to the 8 years, basically 10 million years, 100 million years, and here 10 million years. So some of these stars are very short lifetimes, whereas down here they last practically forever. So the Sun will start to run out of hydrogen in its core in a few billion years' time. Okay, what happens then? Well, this is where it gets interesting. Let's have a look. What happens when the hydrogen starts to run out? Well, a whole little sequence of operations. As the hydrogen runs out, the rate of the energy production falls because there's not as much hydrogen. But remember that pressure balance? If that rate of energy production falls, the pressure balance is upset, which means that the core starts to shrink. as the core shrinks, it gets hotter, which increases the rate of nuclear reactions again. Okay, that ultimately halts, at least temporarily, the collapse of the core, but the outer layers of the star are pushed off. The outer layers of the star actually expand. Here's that Hertzsprung-Russell diagram again. Now actually what I've just described is a rather simplified version of a rather complex sequence of events, but the Sun would now start to move off the main sequence and up here. As the outer layers of the star expand, they cool, turning red. And that means that the inner solar system will change from looking something like this to something like this. Now the Earth may, or may not, just survive this process, but either way it has to be said it won't be very pleasant. As I said, don't lose sleep over this. This is a few thousand million years away. And the spectrum of the Sun now changes. It's now one of a cool, what's called an M-class star, spectral class M. Now eventually, remember that contracting core, the contracting core gets hot enough for some new nuclear reactions to start up. And these nuclear reactions convert helium into elements like carbon and oxygen, and as I said, the contraction of the core now halts for a while. And the Sun is now what's called a red giant, because it's red and big. Now, remember when I said that most stars are just points of light when viewed through the world's largest telescopes? Well, that's true, but there's a small number of them that can be imaged using more than one telescope via a technique that's called interferometry. And here's one. This is an image of a red giant star. It's called Pi 1 Gruis. And these brighter areas on that are actually the tops of convection cells. Remember when I showed you the picture of the Sun yesterday, there's this granulation, these little cells coming up. Well, these are a sort of giant version of that. These are about 120 million kilometres across, so almost the distance of the Earth from the Sun. So this is really big. So what does the Sun look like when it's a red giant? Well, it's something like this. Okay, we've got the core. Now actually I've had to exaggerate the size of the core a bit so that you can see what's going on. The envelope is much bigger. So in the core we now have carbon and oxygen forming. Remember, the helium is being turned into carbon and oxygen. Around that we've got a shell of helium that is being burnt, if you like, turning helium into carbon and oxygen. Okay, and outside that we've still got some hydrogen burning going on, still turning hydrogen into helium, and so on. And then the outer layers of the star, this hydrogen and helium envelope. So it starts to look a bit like a sort of onion. We've got all these different layers going on. So here's another Hertzsprung-Russell diagram, same sort of thing. The Sun's moved up, red giant stage, and this here we have helium burning starting. And then it actually contracts slightly for a while. The problem is that the helium doesn't last nearly as long as the hydrogen did. Okay, the Sun sits on, or will sit on, the main sequence for a total of about 10 billion years. In other words, another 5 billion or so from now. And it's moved from here to where the helium burning starts up, takes about a couple of billion years. Okay, but once you've got helium burning going and final expansion, this lot takes more like 200 million years. So it's very quick. And this increase in size here happens because of basically the same thing that happened with the hydrogen. The helium starts to run out. and eventually the Sun climbs the way up here, increasing in size yet again to somewhere beyond the orbit of Jupiter. And ultimately, in fact, the core and the outer layers of the Sun will part company, and the Sun is now what astronomers call a planetary nebula. This is a confusing name, it's got nothing at all to do with planets. But here's a classic picture of one. This is M57, the Ring Nebula. And what we've got left now is the core of the star, here, and what was the outer layers of the star. And this core of the star is small and white, and in fact is now a white dwarf down there at the bottom left of the Hertzsprung-Russell diagram. Now, not all planetary nebulae look like this. They come in all sorts of different shapes and sizes depending on the dynamics of the star. Here's one, and another, rather pretty that one, and one of my favourites, this one. So, the core of our star is now down here amongst the white dwarfs. And its size now is a little bigger than the Earth, but some 200,000 times more massive. So it's very, very dense. A teaspoonful of white dwarf would weigh about a ton. What happens to the core now? Well, it just slowly cools down. It'll take billions of years to cool down towards what is the Sun's present surface temperature. And remember, all of this we've learnt from Starlight, with the application of nuclear physics and a bit of thought. So let's push our luck and ask, what happens for stars that are more massive than the Sun? Now, these stars have a sufficiently massive core that when the helium starts to run out, it becomes hot enough eventually as it contracts for new reactions, new nuclear reactions, turning carbon and oxygen into heavier elements. In fact, neon, silicon, and ultimately iron and nickel. Once it's got to this stage, the star now faces an energy crisis. The core is hot enough now for reactions turning iron and nickel into heavier elements to start. But these reactions, unlike all the previous ones, don't release energy, they consume it. This is a disaster for the star. Remember that pressure balance holding up the core? Well, once you start these nuclear reactions, that just goes. And the core collapses, and in fact it collapses in a time scale of seconds. The outer layers of the star follow it, and they feed the reactions going on as more and more heavier elements are produced. The whole lot sort of bounces, the star explodes. And the result is one of the most massive explosions known in the universe. Fuel that could have powered the star for millions of years is used up in a few seconds. For a few days, brightness increases 1 billion-fold. The star could outshine an entire galaxy. The outer layers are blown off at something like 45 million miles an hour. Astronomers call it a supernova. Here's one. Here's the galaxy. It was about 240 million light years away. And here's a picture, close-up view of the centre. There's the centre of the galaxy, and here's a star that's gone supernova. Notice it's outshining the entire rest of the galaxy. And this is an X-ray picture. And in fact, this one was one of the brightest supernova ever recorded. And it happened as we saw it in 2006. And this star, the star that blew up, is reckoned to be well over 100 times the mass of the Sun. Supernovae are actually quite rare, although quite rare as seen in our galaxy. there's only 5 been observed in the Milky Way galaxy in the last 1,000 years. This is the remains of one that was seen on Earth in 1054, and records stay that it was visible in daylight for 3 weeks. This is the Crab Nebula, and in fact it's still expanding outwards. These sort of splattered remains of this star, and it's expanding outwards about 1450 kilometers per second. Other supernovae. Here's the remains of one. This is the remnant of a supernova in the constellation of Cassiopeia, and based on its expansion rate it should have been visible around the year 1667, more or less about the time when Newton was thinking of gravity, but it wasn't recorded. To radio astronomers, this supernova is known as Cassiopeia A, and with the exception of the Sun, it's actually the strongest radio source in the sky. Another one here, the Cygnus Loop, the remains of a supernova in the dim and distant past. So, supernovas blasts a large part of a star's matter into space, but the core of the star can still remain, and if it's still more than about 1.4 times the mass of the Sun, then actually it gets compressed beyond the white dwarf stage. Subatomic particles sort of merge together into neutrons, and the collapse is finally halted by a sort of quantum mechanical principle called the Pauli exclusion principle that keeps the neutrons apart. And astronomers call it a neutron star. And here's an example. This is actually the neutron star at the centre of that Crab Nebula, and it's about 11 kilometres across. And a teaspoonful of neutron star, remember a white dwarf teaspoonful would weigh about a tonne, well, a teaspoonful of neutron star weighs 100 million tonnes. If you could stand on the surface of one of them, which admittedly you couldn't, but if you could and sort of drop something, that by the time it hit the surface of the star it would be going about 4 million miles an hour. The gravity is enormous. So here's another image of the heart of the Crab Nebula, and the neutron star is actually the right hand one of the two bright ones to the right of centre, so it's sort of here. And the blue glow inside the sort of shell of red swirling gas is caused by electrons spiralling in at close to the speed of light, because the neutron star has an enormously powerful magnetic field, and in fact this particular one is rotating very fast. As something collapses in, it rotates faster, and this one's going 30 times a second, and you can actually hear this using a radio telescope. So here's the sound of the neutron star at the heart of the Crab Nebula. Other stars that are likely to go supernova is this one. This is Itacarino, and is the only known star to produce ultraviolet laser emission. So anytime soon this one will go, and you notice it's already chucking out loads of material. Betelgeuse in Orion is another candidate, sort of reddish star, top left of Orion, and this should really be quite spectacular when it goes, because it's relatively close, and probably any time in the next billion years or so. Okay, what happens to very, very large stars? And that's when the remainder of the core of your star is more than about 3 times the mass of the Sun. And for these stars, the sort of quantum mechanical pressure that I mentioned previously actually stops the star from collapsing any further is insufficient. It can't halt the collapse, and there is now no known force that can stop it, and the result is a black hole. but I'll talk about black holes in a later talk. Now, supernovae are actually quite important for us because they are responsible for spreading heavier elements around the galaxy. When they blow up, they sling all sorts of stuff way out into the rest of the galaxy. And in fact, there's evidence in the ocean crust on Earth. There's a radioactive isotope of iron-60, and this is produced in abundance by supernovae. But it would have decayed away by now if it had been part of the Earth's original makeup. So that implies that one or probably more supernovae between about 3.2 and 1.7 million years ago, somewhere within 300 light years of the Earth, went off. And these would have been comparable in brightness to the Moon. So it would have been really quite spectacular. So in summary, we have the following as to what happens to different sized stars as they age. So down here, the very lightest stars, brown dwarfs, basically stay as brown dwarfs. Red dwarfs stay most of the time as red dwarfs and eventually end up as a white dwarf, a bit like the Sun will. For stars like the Sun, they actually go through a red giant phase, planetary nebula, and to a white dwarf. And then bigger stars tend to blow up in one way or the other. Supernova, or a particular type of supernova, and either form a neutron star or a black hole. Although it's thought that some, these big blue supergiants, one may just have been detected recently, will collapse directly into a black hole. You don't actually get the supernova, and the very big ones still produce a supernova but are totally destroyed, so you don't have anything left. Now, what's important about this is, as I said, that a supernova blows all sorts of material out into the galaxy. Now, the Sun itself is actually a second generation star. Before it, there were a whole series of bigger stars that went through their lives very quickly, blew up and spread their material out through the galaxy. And in fact, the Sun, and hence the Earth, has quite a number of what's called heavier elements in it, which were not there in the original makeup of the galaxy. These heavier elements have been formed in previous stars. So there are bits of us that formed in stars and supernovae long ago. And in fact, recent simulations suggest that up to half of the atoms in our bodies actually originated in supernova from smaller galaxies even outside the Milky Way. So there you have it. We're nuclear waste. Tomorrow, next talk, I will ask the question, is the Earth alone? Thank you. Okay everybody, I hope you enjoyed that one. As I said, the next talk is the Earth alone? And this will look at exoplanets, planets outside our own solar system, planets around other stars, and ask the question, are there any more like that, more out there that look like the Earth, and is there possibly life out there? See you then.